All right, section 4.6, arithmetic sequences. So our objective for this lesson is to be able to write terms of arithmetic sequences, graph them, and be able to write them as functions, meaning come up with the equation for them. So first we need to talk about what a sequence is. Okay, so first of all, a sequence, okay, just the definition of a sequence is an ordered list of numbers. Ordered list of numbers. Okay. What we mean by ordered is the order in which we list them matters. Okay. So for example, a sequence would be 5, 10, 15, 20, 25, ... Okay, and that keeps going on. And what we mean by ordered is this one is the first one, this one is the second one, this one is the third one. Each of these numbers in our sequence is called a term. Okay, so each number is called a term. And we refer to these numbers by their position in the list. So this one is the first term because it comes first. This one here would be 1, 2, 3, fourth term because of its fourth position in the list. And since we're referring to an arithmetic sequence, which we're going to talk about what makes this sequence arithmetic here in a minute, we're going to refer to each term as the letter A. So when we just say A, that means we're just talking about some random term. So here, if I just use the letter A, we're talking about some random term. Okay? So A just means any of the terms. And then what we do is we use a small number, we call it a subscript, okay? And it's a little number down in the corner. So, okay, I'm gonna show you here. We talked about this 20 being the fourth term. So I would say, okay, so the term that's in the fourth position, so I'm gonna use a little number 4 down in the corner. So we read that as A sub 4. Or the fourth term is equal to 20. So this is just some mathematical notation to help us know like what term we're talking about. And if we don't know which number term we're talking about, then we use a lowercase n. So here I would do A sub n. All this is referring to right here is talking about the nth term in a sequence. Meaning we're talking about some random term in the sequence. We don't know where that term is. Could be the 5th term, could be the 20th term. We don't know, okay? So it's just different, just a different way in which we do notation for sequences. So this was A sub 4 or the 4th term in our sequence. What makes it an arithmetic sequence is that the difference between each pair of consecutive numbers is the same. So we say it has a constant difference between consecutive terms. Okay? Hey, what we mean by that is if I go from first term to second term, one right after the other, the difference is the same. So the difference between this 5 and this 10 is 5. Because if I take the 10 minus 5, we get a difference of 5. The difference between this 15 and this 10 is 5. The difference between this 20 and this 15 is 5. It has that constant difference. If I subtract one term from the term in front of it, I'm always going to get the same thing. And that difference is what we refer to as the common difference. In this case, this common difference, which a lot of times we use lowercase d, the common difference is 5 for this one here because it's the difference, of course, the difference between two terms. Okay, so this sequence, 5, 10, 15, 20, and then a lot of times we go ... which means the sequence keeps going for forever. We're just not going to list it forever. The common difference here is 5. So to determine whether a sequence is an arithmetic sequence, not all sequences are arithmetic sequences. For example, the sequence 1, 2, 4, 8, 16, 32. This guy here, it has a pattern. I multiply by 2 each time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. But the difference between each, the difference there is 1, the difference there is 2, the difference there is 4, the difference there is 8. This one is not an arithmetic. It's not arithmetic. It's not an arithmetic sequence. It's a sequence, but it doesn't go up by the same amount each time. So to write the next 3 terms of an arithmetic is another way of pronouncing it, arithmetic or arithmetic. I kind of bounce back and forth between the two. Here with this arithmetic sequence, very first thing you need to do is find the common difference. So I need to look here, what's the difference between these two? To go from -7 to -14, here we're going down by 7. Okay, if you're not sure, subtract them. -14 minus a -7, that'd be -14 plus 7, which is -7. So I go down by 7. Here I go down by 7. So then now I just need to keep going down by 7. So if I'm at -28 and I go down by 7, that'd be -35. Okay, go down by 7 again, -42. Down by 7 again, -49. It says write the next 3 terms of the arithmetic sequence. There are the next 3 terms. So first step, find that common difference, and then extend that pattern. Okay, so when we graph an arithmetic sequence, we graph it based on our position. Okay, so here's an arithmetic sequence. This is the first term. This is the second term. This is the third term. This is the fourth term. So we're going to graph those as my x and my y. My x is going to be the position, and the y is going to be the actual value. So when I graph these, grab my ruler, okay, I only need positive x's because we only start with first term, second term, so forth and so on. Okay, and it looks like all my terms here are positive 2, 4, 8, 12, 16. We can tell they're my common difference there. It goes up by 4 each time. So I think I can stick with only positive, so I'm going to move my axis down here now. Okay, so we have let's label my axis. First term, second term, third term, and I don't know, we're going to count by 2s maybe here. 2, wait, if we go 2, 4, 6, 8, 10, 12, 14, 16, yeah, that'll work. Okay, just mark a couple out. So the first term was 4. The second term is 8, 2, 4, 6, 8. The third term is 2, 4, 6, 8, 10, 12. The fourth term there was 16. 16. Okay. So there we graphed it. And these are just dots. You do not connect the dots. Because this is not what we call a continuous function. Do not connect the dots. It is not continuous. Meaning I can't have a half term. Okay, it's not continuous. I can't have a half of a term, meaning I can't have an input of like 1.5. Can't have that. But one thing we notice is these all fall on kind of a line. If I was to connect the dots, they all land on a line. The graph is linear. What do you notice? The graph is linear. So we can apply all of our previous linear knowledge from the previous parts of this chapter to arithmetic sequences. Okay, again, we don't connect the dots and draw the lines, but we can use it to help us write equations and graph them, so forth and so on. So we can use that information to determine whether a graph represents an arithmetic sequence. So here, if we notice, these all graph a nice line. If I was to connect the dots, they all graph a nice line. And first term's 15, second term's 12, third term's 9, fourth term's 6. So if I do the common difference here, this one from first to second term, it goes down by 3, 15 to 12. This one, 12 to 9, goes down by 3. This one, 9 to 6, goes down by 3. So does the graph represent an arithmetic sequence? Yes. to explain what? It has a common difference. Okay, I now want you to pause the video and do page 214, 4 through 30 even.